All right. So I think most of you guys are aware of this concept in math that happens sometimes where you're looking at something and it appears linear and you zoom out a little bit and you realize it only appeared linear at the perspective you were looking at it from. And in this case, it's quadratic. In other cases, it could be exponential. So today we're going to talk about um, we have this model of growth for exponential. Here's an example of exponential growth. We're going to talk about a different type of growth called logistic. But um, before we do that, the differential equation you'll be able to tell for some kind of exponential growth, and this makes sense, is dp dt, the change in population over time, is some constant value r times the population. Okay, and the definition of exponential growth is percentage-based growth. A percentage is something that you multiply. Okay, so this thing should make sense, and you should be able to, separate and integrate and get to this equation here. Now, what you might, like a scenario you might encounter, we always talk about exponential growth. You hear this a lot, but in an environment, in an ecosystem, an organism is going to get to a point where it's used up all its resources. And what we may expect to happen, rather than for the rate to keep increasing, is for it to plateau at some peak value. And so when you have growth where there's a period where it's very flat, and then it starts to increase, and then it hits an inflection point, at which point it starts to decrease, and then it flattens out again. And you think of it reaching some high water mark or some carrying capacity, that's called logistic growth. Okay, so the logistic growth, the differential equation, is going to look something like this. And you think of dp over dt is equal to r p times 1 minus p over k. So think of what's going to happen in this case. And let's think of when I'm at 0, okay? When population is 0, okay, the line is going to be really flat. As it increases, right, this, you have to think of, we're multiplying this thing by this thing, right? As population increases, the slope's going to increase a little bit. What's the highest this part right here could ever get? Well, when this part gets to 1, my slope is going to get to 0. So if there's some value k up here, as my population approaches that value k, it's going to start to flatten out again. And so you get this exponential or logistic growth. And this is really, in essence, what you need to understand. Like most of the problems with logistic growth are going to give you a differential equation like this, and they're not going to ask you to separate and integrate. They're just going to ask you to use context clues and figure out what this carrying capacity is. Sometimes they're going to ask you, at what point is the rate of growth the fastest? And that's going to be exactly in between. And it's usually going to be 0. 0 is usually going to be the floor, because this is often going to be contextualized in some type of population problem. And the ceiling is going to be k. It is possible. You can do this. I've done it before. I've learned the hard way that it's not something that you're ever really asked to do, but it is possible to separate and integrate this problem, and you get this kind of, I would say, hot mess of a problem here. I'll show you that it can be done, not by doing it by myself, but I'll just scroll through. These are all the steps that it took. This is, if you search logistic growth and you go to mathlibretext.org, very good site, you can see that it ain't easy, but it can be done. Okay, this is the formula that you're going to get, where this is the carrying capacity and this is the initial population, and those are really the only parameters that are involved, where r is the rate. But what I want to show you is just a tip of like what you can do just with these logistic things. If you know the pattern, oftentimes you can save yourself a lot of work. So they're problems that could go one of two ways. You could go really long down this road trying to separate and integrate, or you could just, a lot of times, like in this case, this first one you may think is logistic, but it's not logistic because it has to have the same, it has to be y here and y here, okay? This one is logistic. It's 2y times 3 minus y. You might immediately think to yourself, the low water mark is 0, the high water mark is 3. And the questions might say, find the limit of g of x as x approaches infinity. As x approaches infinity, that's saying as time moves on forever and ever and ever, and that's when it's going to be hitting its top, its upper level, which is 3. And it might say the limit as x goes to infinity of g prime of x, and that's as it goes on forever and ever and ever. It's logistic. It's 0. And for what values of g for what values of y does g have a point of inflection? Find the slope of the graph at the point of inflection. It's not necessary to solve for it. Well, in that case, you might realize that this is when y is equal to 1.5. Notice there's no x in there, so there's nothing. You don't know what year it is or anything, but when y is equal to 1.5, what would it be? 3 times 1.5, like 4.5 maybe. So 4.5. There it is. So this is one where if you are aware of how they're often going to ask you questions about logistics, you can save yourself a little bit of effort.